Uh, Good afternoon, everyone. Thank you, Jan, for the presentation. I'm not a professor yet, but I will be.
We hope to.
So this is the title of my talk, Close by One Strategy for Computing the Fuzzy Concept Lattice. This is within the framework of FCA, Formal Concept Analysis. And this is a brief table of contents of what this is going to be about. First, little introduction and motivation of the problem we're trying to solve. Then some literature review of algorithms to compute the concept lattice and the problem in the fuzzy setting. So in classical FCA, we have a binary table of data, which is a formal context, the so-called formal context, and there are two complementary entities, or knowledge entities, that are the concept lattice, which is algebraically a lattice, and a basis of context palette implications. Well, the concept lattice gives exhaustive analysis of all the hidden or implicit knowledge in the formal context, and the formal concepts are the closed sets of objects and attributes in this setting. The number of concepts in a context can be exponential in the worst case. And determining this number is a p-complete problem. Okay. This holds in the binary case, but when we use intermediate truth values and truth value structure such as finite lattice, it's much worse. So this is an example of a fuzzy formal context. In this case, the truth values are 0, 1/2, and 1. And this is one of the approaches used by Belolavec and Konechny that scales in some way the context in order to compute the formal concepts in a crisp-like manner. Notice that this context is not crisp, but it behaves properly for applying the crisp algorithms. Well, these should be references, but I will just say them. So before the introduction of FCA in the literature in the 78, Norris already published a paper determining the maximal rectangles in binary tables. This enters in the field of if-then rules in binary data sets and is not FCA, but later in 1982, FCA was introduced, and all this framework could be reused for this setting. Next closure algorithm was devised by Bernard Ganter, where he introduced the lectic order in the subsets of attributes, and it was an algorithm with polynomial delay. So even though the problem is NP complete, the algorithm has polynomial delay, which is not as bad. Lindy's next neighbor is was another big leap in the computation of the concept lattice, and at least for us, the close by one, from now on CBO algorithm devised by Kuznetsov in '93 was a very big step, because instead of computing the whole lattice, it just computes the set of formal concepts, and the order can easily be defined later. So instead of building the whole lattice, it turns the problem into a search tree programming kind of problem. And from that moment on, we have a search tree, and the strategy is now how to prune the tree to optimize the algorithm as much as we can. Well, Krajca in 2010 already said that the main problem with these algorithms was redundant computation. We had to make the same tests again and again, when maybe we already know that the test is going to fail. So he devised the fast CBO algorithm, which did exactly that. Whenever a test failed, then every children would also fail the test. So just skip those iterations. On another line, the enclosed family of algorithms by Andrews originally introduced in 2017, they introduced an incremental computation of the closure. So instead of computing the closure all at once, we only compute it until the attribute we are at the moment. So this also reduces greatly the cost of computation because computing closures is one of the most costly operations that we do in FCA. So in the fuzzy setting, we don't have only 0 and 1 as truth values, but we will use a finite completely residuated lattice, and a formal context is going to be a tuple with G, the set of objects, M, the set of attributes, and I will be a fuzzy relation that goes from G times N to L. And the concept forming operators are defined as such. They are the intent and the extent, but from now on, for the sake of presentation, I will just say up and down, okay? Up and down. The definition is like that, which is a direct extension of the definition in the CRISP case. If you're used to FCA, it will be very natural to you. If you're not used to FCA, this will be a little monster, but it's okay. This is just up and down from now on. The pair up and down forms a fuzzy Galois connection, which is a structure we're going to take advantage of from now on. So in the fuzzy case, the only algorithm that has been properly extended has been the next closure algorithm. The rest are used by scaling and wrapping the algorithms in the CRISP case. This is a strategy used by Violonave and Konechny in their paper in the IEEE conference in 2017. Our proposal is to refactor the CBO family of algorithms in a native fuzzy way. What is the CBO strategy? Well, we start with a given concept. And now, from this extent A, we build the extent C for each attribute just by intersecting this. Since up and down is a fuzzy Galois connection, we know that this is also an extent, and the intersection of extents is an extent because it's a closure system. So this is indeed an extent. If the extent is the same, skip the operation, skip the iteration. If it's not, it's a new extent, and we can compute its intent, and this is a new formal concept. We can run this strategy until it stops, and it terminates and computes all the formal contexts, all the formal concepts exactly once. We only need to set as the first concept the whole set of objects and its intent, which is always a formal concept, and it's also the biggest one. So we start here and iterate this, and it just keeps on giving formal concepts. And the several improvements we said before are, again, applicable in this case. Fast CBO, enclosed 2, 4, or 5. The concepts, the child concepts, are computed in this manner. In this pseudocode, you can see the code. The only difference between the CRISP case and the fuzzy case is this loop, because now we don't need to loop around all the attributes, but we also need to run through all the possible truth values. So that, and we don't intersect with the intent of attributes, but each intent, the extent of each attribute and each truth value. So with this little difference, we have defined a native fuzzy CBO algorithm. The rest of improvements can be done exactly the same as in the CRISP case with slight modifications, but they are very natural. And these are the CRISP strategies used in the fuzzy case, but there are native fuzzy strategies that can be taken advantage of. So for example, look at this case. Just assume the truth values are the quartiles, 0, 0.5, 0.5, 0.75, and 1. And this is the formal context. Very small formal context, only for the example. We start with this candidate concept. This is not a concept, but it's a candidate. The next attribute is A. Of course, there's only A. The next truth value is 0.5, which is this, the first non-zero truth value. We do C, we compute it, and we compute its intent, and it's not the same as the candidate. So the test has failed. So according to the algorithm, we should use the next truth value. But we already know that the truth value must be 0.75. So why should we do this iteration? We can just jump to 0.75 and skip this. And indeed, this is a valid strategy. The algorithm using the jump terminates, computes all formal concepts and only once. And let me just give a little details about the difference between native fuzzy algorithms and scaling and wrapping algorithms. Well, as I said before, Bieloglavek and Konechny introduced scaling in 2017, and they applied CRISP, formal context algorithms, to the scaled ones. Well, the problem is that we lose the semantics of having different truth values. When you scale, you consider different truth values as completely different attributes. So you are losing the meaning of having a higher or lower truth value. So instead of having a little search tree as this one, we start from nothing and we check all 4 possible truth values. If we consider them as independent attributes, we would have a search tree like this, because you have to check each one as a independent one. There's no relation amongst them. So you need to check all these subtree, all this subtree, and this subtree. So the computation is heavily charged when we lose these semantics. And here we have some experimental results. And you can see that the enclose with the wrapping strategy is here. It computes the most number of tests, and also it's kind of tied with FastCBO in the number of computation of intents. We can see the pink line, that is the enclose 5 with the jumping strategy, that it computes less tests and less intents. And also in general, that native fuzzy approaches improve the scaling approach. This is an analysis on the number of attributes, but we have also done the analysis on the number of truth values in the lattice L. And again, the enclose 5 with the jumping strategy improves all the others, and wrapping is in the worst case scenario here. This is the wrapped and scaled algorithm. As expected, next closure is one of the worst algorithms because it is very, it computes heavily and does a lot of redundant computation. And here is an analysis on the density of the context. And again, even though it is much more similar in this case, enclose 5 with a jump is better than the other algorithms, and wrapping is against one of the worst case scenarios. Here is an analysis on time. It is enclose 2 with the wrapping strategy, with the scaled algorithm, and we can see that the difference is very significant with the native fuzzy approach, and even enclose 2 with the native fuzzy approach is improved greatly with the enclose 5 pruning strategy and the jump. Again, when the case is worse, so we have a bigger table with a big number of truth values, notice that enclose 2 with the wrapping strategy takes a long time, which is basically more than 10 times more than enclose 2 with the native fuzzy strategy. And again, the enclose 5 with the improved pruning and the jump gives almost half of the time of this enclose 2 algorithm. So we have introduced native fuzzy strategies for computing the concept lattice, and the adaptation in the fuzzy setting requires a partial canonicity test and a restructuring of the search tree. We provide examples, and they show that how the performance is improved with each of the more sophisticated pruning strategies. And as future work, we would like to adapt the algorithms to also give the basis of attribute implications and consider the importance of ordering the attributes, either only the attributes or the whole context, to get faster computation in these kind of problems. And that was it. Thank you very much.
So once more, we have 10, that's enough, but we have time for questions. So please ask. Not, I will ask.
Yes.
So my question is, that's only computation of, say, closed sets. But what about pictures?
Sorry?
What about pictures, diagrams of
Okay.
how quickly can you make some picture or?
Yes, actually we used fsta package for the implementation.
So the same as Villa and so on.
Sorry?
So the same as Villa, Ganta, and so on.
Yes, yes.
Yeah.
The picture are the same, but we use our own package. It's an R language package for the computation of all these strategies, and it admits crisp, many-valued, and fuzzy computing. So yeah, we are using our own package where it's strongly based on the Connext and all the other known libraries.
So thanks. Some other questions? So if not, we have 3 minutes break.
Okay.
Thanks.
Okay. 2 minutes. I will have 2 minutes more.
Oh, yeah. If you like.
No, I don't think so.
So we will continue immediately because your colleague would like to have 2 minutes more. So please start. It's a 4 title question.
Okay. Well, hello, everybody. Thank you for coming. I'm going to talk about my joint work with Andrei Kritlo from University Paul Joseph Safari here in Slovakia, Domingo Lopez, which was also a co-author of the previous talk, and Marek Reformat from University of Alberta, Canada. The title of the talk is a formal context-based approach to expand RDF data. This is, so to say, RDF. Sorry? RDF, what does it mean? Yes, well, I will resource description framework. Oh, I will later. I was saying that this is a kind of experimental work done on some theoretical publication we have recently had on the field of formal concept analysis. In this paper, in this talk, we focus on the process of building a connection between RDF, which is the resource description framework, in order to represent the information, and the framework of formal concept analysis. The approach would involve transforming a general graph in which vertices represent objects and the edges are relations between these objects into a series of bipartite graphs, which can be interpreted like a formal context, and then FCA comes into play. This is achieved by separating edges that represent the specific relationships by providing a clear representation of the underlying knowledge. Let me, please. Okay, in the presentation, we will recall a little bit the theoretical part that has been done in these two papers, and then we put it in play by using a toy example. The idea is to consider an RDF graph, which can be seen like a representation of the knowledge contained to a domain. And then we are not claiming that our strategy would be used or could be used to improve or to complete the graph. Now we are assuming that the graph is complete or has the most information that can be obtained, but could be used, for instance, to try to infer extra information depending on some external input. I will enter a little bit into the details in a few slides. And the idea of this talk is that we see that this approach could be useful for some applications, including data analysis, knowledge representation, and the like. Okay, in these two papers, one by our Slovak colleagues, Andrej Krytlo, Lubomir Antoni, and Stano Krajci. And this is a joint work between Košice and Malaga. There were some strategies in order to introduce bonds. Bonds is a technical term from FCA, which links to different formal contexts. In order to use them for recommendation tasks. Based on this paper in last year, actually, it was extended a little bit with the use of external information. What does this mean? So let me put the problem into context. This is related to the fact that a bipartite graph can be seen as a formal context. This is obvious. But once you notice that, okay, then I can try to apply FCA to some kind of a graph theory, so to say, and see what happens. Well, here in the FCA, there are two possibilities to construct the concept-forming operations. One has been presented by the previous speaker. It is this one, but I have written this in the CRISP case. This is the antitone or version of the concept-forming operators, which were the original ones used by Bernard Ganter and Rudolf Wille when introducing FCA. Then there is another one, which is the isotone, which is based on a different interpretation of the notion of concept we want to obtain. Let me go back. In the usual one, the intent is defined as a subset containing all the adjacent nodes to the given node. I'm talking now in the graph terms. The isotone intent, so to say, is formed by all vertices that are adjacent to some, not all. Then here the definition changes from the universal quantifier to the existential quantifier. And then, and also the extent is not symmetrical, have a different definition. Well, now the problem with the bonds. It is not a problem, but I will say that okay, in which kind of theoretical problem we apply this, or actually we, Lubo, Antoni, and Andrej applied. It is related to the composition of graphs or relations. Martin gave a plenary speaker in the EUS flat last here, and well, this is closely related to the fuzzy relational compositional operators, and even the isotone and the antitone construction can be rewritten in terms of those. The idea is that imagine we have two bipartite graphs. One is this, one is that, which are composable in terms of relation. It means that the domain, the codomain of the one is the domain of the second. And then by applying the universal definition, the composition would be like this. That means that this vertex is linked to this, provided that if every path starting from here can get. And this one would be the existential one. Sorry. Yes, yes. If yes. Starting from all these these edges, you can get in this here. No, there's no problem. But here we have to then, if it is possible to go here from this, yes, and from this, yes, then if they are. This is somehow we have used the rigorous approach, and then there is another, the benevolent approach. We say, okay, we link together if some path can be built from one to the other. It is a segment. There is nothing new here, simply restating what is known. Now, what happens? Talking about composition of graphs. This is a strict, very strong requirement. What if we would like somehow to compose two graphs or two relations which are not composable? For instance, imagine something like this. One and the other. Okay, you cannot compose. But now the idea is, what if we can obtain extra information linking the codomain with the domain? Imagine this does not exist. And then we are trying to link, to compose this bipartite graph with this one. Okay, you cannot because they are not linked. Okay, then we obtain external information and we have this. Now, here, looking like a kind of a ternary composition, we can obtain again, the rigorous are the benevolent or the universal or the existential composition. Okay. This can be reproduced or this can be formalized in terms of constructs of a formal concept analysis. This can be, now let me back. This can be formalized as the concept forming operators associated to particular new formal context or the product of the implication. Here it is a formal context, another formal context, and this is a new formal context. If we apply then the up arrow there, we have a isotone formal concept operator associated to the product. Okay, something like that. And then this is represented here, and that is represented. Well, all of that was more or less the content, the theoretical content, apart of a number of more things of the two papers we commented before. And now, what about RDF here? Okay, RDF, for those who don't know, is a resource description framework, which essentially is a formal term to refer to a graph, essentially. In a graph, we have different objects and different relations. That's it. I'm sorry if there is somebody from the computer science thinks that it is something more different. I don't see the difference. For instance, something like this. This could be a fragment of RDF called creative work. Okay, then we make publications. Each publication have an author. There are some keywords. Occasionally, some paper gets citations, and then there is a between papers and papers, and the like. Well, it could be possible concentrate on a subset of this RDF graph. For instance, consider we have there 4 papers, P1, P2, P3, P4. And then here we have information about authors. Betty is the author of P1, and John, both are co-authors, and the like. Okay, and this could be a snippet of the graph. But we cannot use this directly. We need the bipartite graphs. And this is not bipartite so far. Okay, then assume that we have our graph and we have a particular problem which requires us to somehow compose some existing relation in the graph. We could, for instance, be interested in, let me go back here. No, back, no, therefore. My problem would be that I am organizing a conference and I have to prepare the reviewing process. For the reviewing process, I receive a number of papers and I have to assign reviewers to these papers. But I shouldn't do this randomly, but thinking that this paper should be reviewed by something knowledge with the knowledge of the content of the paper, right? Something that sometimes doesn't happen. And in any way, it is difficult to find them. Okay, wouldn't it be possible to somehow formalize this? Okay, then let me go back from kind of this snippet. I am interested, for instance, in extracted information about which topics are known to each author. Then I could link authors with the keyword with the keywords of the papers have been authored by him or her, for instance. Then we obtain something like this. This is quite useful if I want to assign papers to reviewers. I have to have this information. If not, okay, this could be external information to put into the system, which is the brain of the program, the chair or of the conference or something. Okay. Then the idea is exactly that. I have some theoretical machinery which is able to join 2 bipartite graphs. And in some cases, I need some internal information or external information to put inside to glue together the domain and the codomain. And in that case, I could make the composition. In this case, in this toy example, the composition would be the assignment of papers to reviewers. The better, the more precise. Then here, for instance, we will need some information. That would be the graph containing the links between authors and keywords. A graph describing the new submitted paper with keywords. This is quite easy, but because every paper should have this topic, and this topic. And then a piece of external information, which is the mapping between the keywords, which can be exactly the same or from the same set, or can be similar. I mean, for instance, we can have 6 potential reviewers here, and there are several topics: fuzzy FCA, cancer Pilates, data mining, machine learning, and the like. And then some of them know this part, some of them know the part. Yes, okay. I have time, thank you. Then there are the new papers, received papers, and each paper chooses 3 topics. But it might happen that the topics used by the authors are not exactly the same, or the terms used are not exactly the terms used by the reviewers. We need some information here. And now what happens? Here, for instance, I have needed to introduce fuzziness here, or at least a multi-valued. Why? Because, for instance, topic J, hierarchy or a fuzzy FCA. It is the same? No. It is something completely different? No. There is some relation. Okay, well, let us put some intermediate information, 1/2 or something. Like. Then here we don't have a crisp formal concept, but a multi-valued or fuzzy formal context. Okay. This could also be put in the information of the reviewers. This can be number one, or perhaps there are some reviewers who say, okay, because you should know about category zero. Yes, but that I did that 20 years ago, and then I prefer not to be reviewing those. Okay, then I would assign 1/2 or 1/4 to those cases. Then here, fuzzy or multiple valued fits very well. By using the bond-based composition that we have obtained there, I will not enter into the detail. Then we have that the rigorous and the benevolent provide this kind of very, very different solutions. In the rigorous, we are expecting that each paper is assigned exactly to 3 reviewers, which are very well knowledgeable of all the topics. Very unlikely, but we know. With the benevolent, you say, well, we hope that at least some reviewers know something about the paper, and cross fingers. But well, at least this provides some initial clue in order or to how to assign. Now, future work. Is there something between here and here? Yeah, it should be. What are the possible directions to study here? I will skip the conclusions. I guess they are more or less clear that something can be done using those theoretical tools, highly theoretical tools. But there is something in between. Yes, we are jumping from the universal quantifier to the existential quantifier, and we are in a fuzzy setting. Okay, then we have a number of intermediate fuzzy quantifiers in order to be used and see whether we are able to reproduce the underlying mathematical construction of the bonds by using this kind of intermediate quantifiers. That would be the first future work that we would like to do in order to provide some actual application of the theory. And that's all. Thank you.
Okay, thank you.
So good afternoon, ladies and gentlemen. Yeah, it's my pleasure, yeah, to introduce this topic. It's quite new direction of the research, yeah, and I will explain the motivation and some results about, yeah. So as you see from the title, yeah, this is focused on the proof of Kolmogorov superposition theorem, and to reconsider this proof from the point of view of the inverse F transforms, actually, yeah. Okay, so let's the very introductive part, because the Kolmogorov theorem is connected with the famous Hilbert problem, the so-called 13th Hilbert problem among all, as you see, 23 problems, and the set of these problems was published in the beginning of the 20th century, and then it gave really feed for mathematicians for next centuries, as you know, and the conjecture was actually the question that was posed by by Hilbert, was about, are there genuine continuous functions that do not somehow depend on functions on one variable. So in other words, are there functions that cannot be represented with the help of functions of one variable and the operation of summation, addition, actually, and actually almost 50 years people, I mean mathematicians, believe that this conjecture is has negative answer. So this means that actually there are functions, and people looked functions of three variables, in order to show that they cannot be represented, using only functions of one variable. And finally, in the year of 56, Kolmogorov proved the surprising results, that denied, the Hilbert conjecture, and so here you see the exact formulation of the Kolmogorov, what is known now as Kolmogorov superposition theorem. I will just read, so for any n means the number of variables, there exist real numbers, lambda 1 up to n, and continuous functions phi k. So this is so so all parameters here, it's interesting. They are mostly they cannot be improved later. It was shown. Where so this I is the denotation for 0, 1, with the property that for every continuous function, maps this I to n to r, there exists a continuous function g such that for each n tuple, this representation holds true. So this is the main focus of this talk, just to analyze this expression, and why it is still interesting for us. First of all, some details, What is important here? Look, it is important that in this representation, the internal part does not depend on the function f, and only j, function j, depends on f. So this means that we can follow the construction of this proof, and actually propose how these functions can be selected, and then we show how, based on this selection, we can define this external function j. So this is the this is very tricky, actually, and actually, now, why this theorem is still interesting for us? Because, there was boom in neural networks, and especially when so-called MLP, multi-layer perceptron, appeared. So as a justification of the correctness of this MLP computation, so people found that their computation is in fact based on the validity of this theory. Actually, as we see here, the construction is exactly what later was put into the computation process in MLP, because here we have n neurons associated with functions phi, then we have weights, and then we have activation. So every component of neural network in this simplest case, yeah, really is here. Yeah, and if you remember, the first theoretical books, they cited this theorem, yeah, in order to justify the work, the processing based on neural networks. Yeah, so this means, yeah, and therefore, you know, so now this theorem was somehow forgotten. Yeah, but and it's a pity, and you know, so but people are still thinking about the problem of explainability of the success of neural networks. Yeah, and you know, so there are many approaches, but practically no approaches are focused on the way of computation. Yeah, they are focused on way on explanation, means how to connect inputs and outputs. Yeah, and just looking. Yeah, and therefore they call that, yeah, it is black box. Yeah, only inputs and outputs are important, and what is processed is somehow random. Yeah, it's not random actually. Yeah, and therefore is if we again just look at this. Yeah, so we will see the meaning, yeah, of all components. Yeah, so I repeat. Yeah, so weights are here, neurons are here, and activation is here. Yeah, and therefore, you know, so yeah, I decided to look into the details, technical details of the proof. Yeah, and when I somehow learned how really it was proposed, yeah, I have realized that there are common points with how say fuzzy people, yeah, approached to proving approximation theorems, universal approximation, yeah, as you remember. Yeah, and therefore it came to my mind that really, so we can show that there is connection, and moreover this connection helps people, in my opinion, of course, yeah, to understand better, yeah, the construction, yeah, of these parameters, because partially these parameters, yeah, are not given in constructive way. For example, the function g, yeah, is a result of the convergence procedure. So this means that we can, this is a recursive procedure. We can characterize first step, but then we just proclaim it converges because it should converge, yeah, in a certain sense. Okay, so yeah, and now, as I said, so my purpose, yeah, is to convince you that yeah, so what is really constructive, yeah, in the Kolmogorov proof is the construction of these functions phi k, yeah, in this case, yeah. But actually Kolmogorov delineated the set, yeah, the set from which we can pick up these functions, yeah, and also it was only partially characterized. Okay, so this is the introduction, and now I will step by step. First of all, yeah, I will show you how the proof is organized just in big steps, and then I will show you the idea which really fascinated me when I analyzed this proof as well. Okay, so here you see the purpose of this talk. Yeah, more or less I explain the motivation. Yeah, and moreover, you know, so this, I mean, in the representation which I will finally propose, yeah, we will see the role of new actually spaces, yeah, which we introduced, and these are spaces with fuzzy partitions. Okay, so yeah, we will be focused on the special case of this theorem, and this case yeah, is tailored for functions of two variables actually. So, and then in this case, the representation inside can be simplified. So it has only one parameter lambda, not two. It's clean. Okay, yeah, and yeah, and actually here we see the constant, yeah, because yeah, previously it was 2n plus 1. So for case 2, we have here 5. Yeah, so parameters are here. Then the necessary denotation is here. I will not read it. It's all more or less understandable. Yeah, the role of lambda. The role of lambda will explain here, and then we will refer to this lemma just to say that lambda is anything that fulfill this characterization. Yeah, actually the role of lambda is to separate. Yeah. So these combinations actually, yeah, because if you remember, yeah, the focus is that to select functions phi and then to define functions j, but j is the external function, and therefore j should be defined, yeah, on a set of distinct points, yeah. And this is the point, how to make these combinations, yeah, inside, yeah, how to force them to produce distinct points, yeah. That's the purpose. Okay. Yeah, and so this important lemma, it is technical lemma which explains the construction, yeah, of parameters, yeah, in the representation. So lambda is fixed, as I said, so f is fixed as well. And then this is important function, yeah, of functions phi k of one variables. But here in this lemma, at the first step, yeah, so the construction depends on f, yeah, and later we will see how to get rid of these dependence. But in any case, the construction will be preserved in a certain sense, yeah. So functions are, so this is very tricky formulation, because first of all, we say that this is set of all functions such that they exist something, yeah, they exist function j with this limitation, actually boundaries, yeah, and such that this expression, yeah, which we now analyze, yeah, has this boundary, yeah. So this boundary, yeah, is somehow you know, very rough estimation. We cannot say that we have approximation, yeah. But later we will see how, based on this, we will organize the convergence procedure. Okay, so yeah, what is important here is just the this characterization. Yeah, look, so the again, I will read, yeah, because this is important. Yeah, so UF is the set of all these tuples such that they exist G. So the existence is somehow assumed, yeah, and this should be fulfilled. And if so all these conditions, yeah, are satisfied, then, and this is important, then this set, yeah, so the existence of this set will be proven, yeah. And this set is an open and dense subset in this set of continuous function, actually functions continuous, these 5 tuples. Okay, so this is the first, yeah, lemma. Sorry, second important. Yeah, the third important lemma is characterizes how we can get rid of the dependence on f of the set U. Yeah, and actually it says that there exist functions. Now, look, yeah, now the existence, yeah, is given up, no dependence. So we start with, so lambda exists, functions exist, and such that given f, they exist G. So now we see that in this formulation, only G, yeah, depends on f, and these functions do not depend. So how we get rid of this? Yeah, this is based on the so-called, I'm not sure that I have it. Yeah, no, I don't have this. This is based on the so-called Beer category theorem, which says that the intersection of open dense sets is again open dense set. Yeah, so this means that if we start with one UF, this set, yeah, and then we construct a set of again open dense subset in a certain way, we will see it in the next slide, then we can guarantee, and actually then we can select these functions from the final intersection, which is again open and dense, yeah. And therefore, yeah, so this is the procedure actually of convergence, yeah, and this is the final just proof, yeah. I will just show you, yeah, the main steps, yeah. We start from the given function, yeah, and select some first G according to lemma 2, yeah, and then we compute the difference, yeah, and then you know, so and then we continue actually, yeah. So this is a new function for which again it is continuous, and for this function we again find corresponding set U, corresponding function J, yeah, and so on and so forth, yeah. And at each step you will work with sets U that depends on functions in this sequence, yeah. But then when we take intersection we get rid of this dependence and we select finally functions phi from this intersection, and therefore we have what we have actually. Yeah, and moreover, so and also the j is a matter of convergence, so it's here. Yeah, I will go into the details because so. Oh, okay, so I will try to manage. Yeah, so what we propose actually, we propose, as I said, to analyze the proof and to show that functions phi k can be characterized with the help of inverse F transforms. Therefore, I recall you the notion of quasi-partition. Yeah, probably, you know it. It's a bit general. I do not have time to go into the details. Yeah, actually, we have partition of now interval 0, 1 with fuzzy sets. We call it generalized because because I will show you a picture. Yeah, so they are not requirements of uniform partition, nothing like that. Yeah, only shape is important. Yeah, and also intersection is important. So this is one example. Yeah, okay, it is here. And then, instead of working with inverse F transform, normally we introduced it for function. Here, it is for sequence. Yeah, actually, this notion was introduced in the paper which is cited below. So if we have generalized fuzzy partition, and if we have sequence of reals, and the number of elements in this sequence is the same as the number of basic sets, then we can compute this function. Yeah, actually from sequence we have function. Yeah, if we apply this expression. Yeah, and so we call this function inverse F transform of the sequence with respect to fuzzy partition. Okay, so now how it works in the proof of Kolmogorov. Yeah, so we use the idea of how functions from the set, this phi k from the set UF was constructed actually. Yeah, look, so Kolmogorov proposed to consider partition of 0, 1 into these 5 sets of subintervals actually, yeah, and altogether they form covering. So technical details are here, yeah, but here, as you see, so you have subintervals, yeah, and actually you have 5 subpartitions, yeah, into these intervals, yeah, and based on this, so I propose to consider fuzzy partition in such a way that we consider fuzzy sets in this partition to be equal on each subinterval and equal 1. Yeah, actually, this is normalized fuzzy set. Yeah, and to go linear, to connect linearly with the points, yeah, where here there is no connection. Actually, yeah, imagine, yeah, so we take, yeah, for example, this subinterval and construct, in this case, trapezoidal fuzzy set such that on this subinterval, it takes value 1, and then it goes to 0 linearly to this point and to 0 linearly to this point. And by this, okay, so probably I will take some more minutes here. Yeah, so so this is the idea. So how from Kolmogorov partition we come to this fuzzy partition. So this is the characterization which I explained you. So how we construct these trapezoidal functions. Yeah. And now actually, if we have, actually in this case, we have 5 partitions. Yeah. And what is important, yeah, it is possible to prove that each partition is actually a partition of unity. Yeah. But altogether, the set of, if we unify all partitions, we obtain the so-called partition, fuzzy 5 partition introduced by Stefanini. So now we have, yeah, so now we have partition. And of course, now we can use the idea of connecting sequence of reals with the inverse F transforms. Yeah, and this, so if we apply this idea, then we can say that this is how functions phi k can be constructed actually. Yeah, so this is the idea which implicitly was used by Kolmogorov in his proof. Yeah, but in Kolmogorov's case, yeah, he left the part that were not covered. Yeah, if you remember, so his partition. Yeah, so subinterval. So at this on these parts, his functions phi k were not defined at all. So they are arbitrary continuous. Yeah, arbitrary continuous. In the case which I proposed, we have linear parts. But also this, what is important is that these functions, I mean, these that have this form of inverse F transform, they also form the open dense subset in corresponding sets of continuous functions. And therefore, we can replace what Kolmogorov proposed by this proposal. Yeah, actually, this is the conclusion, yeah, of this construction. So this new set, yeah, is open dense subset, yeah, in this. Okay, so now
You read a speech by
I will only, yeah, so yeah, you know, so that was only the last slide actually, yeah, but okay, so yeah, in any case, yeah. Thank you.
Irina, don't worry, I will have the same problem like you. It means the time is running. So you can see the title of my talk. This is on approximation of lattice integral transforms. This is a joint paper with my PhD student, Viek Kwok. He defended his PhD thesis last year. So lattice integral transform is somehow generalization of lattice fuzzy transform, and lattice fuzzy transform is lattice version of the fuzzy transform for real or complex valued functions presented in the previous talk. So let's go. Motivation. First, as I said before, we know two types of fuzzy transforms or lattice fuzzy transforms, direct and upper. And you can see here the formulas. Okay. Sorry? No. Two formulas. Yeah, the first one is based on existential quantifier, and here is the multiplication, which is took from some residuated lattice. Here is existential quantifier and residuum. Almost the same, you can see, just we switch like operators. Again, further, we have inverse lattice fuzzy transform, and it can be defined in two ways, again, upper and lower. You can see almost the same or the same formulas. And what is important here, that this definition is based on some fuzzy partition. Fuzzy partition also has been mentioned in the previous talk, and here you can see the example of such a fuzzy partition. But the difference between fuzzy partition, which is used in the context of real functions, this partition must, or cores of fuzzy sets that are used for fuzzy partition must be the standard partition of the set. Yeah, just the boundaries are somehow fuzzy. Okay, so what is really interesting that here we consider in these formulas two partitions. One partition which is used to transform functions from the space fx to space fy, and here we have again another partition which somehow transforms functions from fy to fx. Yeah, and what is interesting is that, for example, here the AI is AI is a fuzzy set defined like here, and the bx is defined in another way. such that AI can be described using some fuzzy relation k xy, and bx is somehow inverse a fuzzy relation when we switch between x and y. The core of the first fuzzy set is, for example, here, minus 1.5, 1.5, but the core of the second, for example, B3, is a singleton. Yeah, so completely different, cores. So, and now in the paper published, published on the conference IEEE, we proposed with my student some generalization of the formulas, and these generalizations are based on Sugeno-like integral, because we know that Sugeno-like integral can extend the existential quantifier and supremum and the universal quantifier infimum for the specific measure which is used here. I will not go to details, but believe me. So, and here you can see that just we use some function which relates x and y to spaces. This function will be called integral kernel. And here is the operation between this integral kernel and the original function to transform it to another space, like in the standard Fourier transform or Laplace transform and so on. And we just switch between two operations. Here is the multiplication from the residuity lattice and the residuum. So the same formula, two different operations. And of course, we need to consider somehow measures that are used to get nice results. What is interesting is how the combination or composition of two fuzzy transforms can approximate the original function. And it's known that the composition of lower fuzzy transforms, inverse and direct, we get like lower boundary or for the original function. And if we compose the upper direct and inverse fuzzy transform, we get like upper boundary for this function. So the original function is between some like lower approximation and upper approximation. But what is in the case when the existential and universal quantifier are replaced by more general Sugeno-like integrals? And we proved like preliminary result that shows that similarly like here, just we use two different measures. Here, the integral kernel, here is like transpose integral kernel, and we get that the composition is greater than not f, but somehow again integral transform, lattice integral transform of the original function, but not to k with respect to k, but some different, a little different kernel, which is defined on the space X. So this is like that. This is greater than some filter of the original function, not original function, but somehow filter using which is related to this integral kernel Q. And similarly, we get in the opposite composition. And the Q is connected to the original kernel and its inverse. In this case, it's the transpose. The Q is somehow compatible kernel with these two kernels on the product of X. So here, just to illustrate the comparison between lattice fuzzy transforms and lattice integral transforms looks like this. You can see that here we get the upper approximation and lower approximation using fuzzy transforms. But in the case of lattice integral transforms, we get something which is not upper and lower, which could, for example, determine some trend in time series. For example, if we have noisy function, you can see that the upper and lower approximation using fuzzy transform is for nothing, because there is no reduction of the noise. It cannot be used like the filter for it. But in the case of lattice integral transform, yeah, we can suppress the noise, or even we can suppress some frequencies, high frequencies, and so on. So lattice integral transforms are some like challenge for new types of filters, for example, in signal processing. So here applications: signal image processing, noise filtering, compression, decompression, even morphological operators mentioned in the paper of Peter Sussner based on lattice fuzzy transforms. There was proof some relation. Would be also modeled using these lattice integral transforms. Moreover, evaluation of alternatives in multi-criteria decision making can be used or can be defined using these leads. So we see some applications, we see some like approximations. But the question was, okay, can we somehow measure the quality of this approximation like in the standard real valued fuzzy transform? Because we are working on a lattice. So what is the construction? So this is here just figures, picture, yeah, opening and closing, for example. Here is fuzzy opening, fuzzy closing. Here is something which is defined using lattice integral transforms. So so the goal of this presentation is first somehow generalize these inequalities, and the second is to find some measure which could estimate the closeness of the original function and its approximation, which is get using the composition of two different lattice integral transforms. Now, several notions, yeah, support core lattice fuzzy measure, which is like a map satisfying these two conditions. And conjugate fuzzy measure is determined using negation and using, sorry, here should be n, and using complement, which is inside of the measure. So this is like new measure defined using measure mu. This is n conjugate fuzzy measure. Let us recall Sukeno-like fuzzy integral. Yeah, this is generalization, supremum over all measurable sets from F. This is the standard sets, not fuzzy sets. And it is the infimum over Fx multiplied by the measure of the set A. Integral kernel is a binary fuzzy relation, which is normal in the second component. So it means that for any y, the core of this function is non-empty. Here is the definition. Right? Compatible kernels, so an integral kernel Q is said to be compatible with K and K prime if we have this inequality for any X and Z and Y. Now, it's interesting that if we have more functions, so more kernels, Ki, that are compatible, also Q is compatible with K and Ki, so the union of these kernels, which are defined in the opposite way, is again, like Q is again compatible with K and this union. So it means that Q can be arbitrary, so but the compatibility is given like here. Now, the question is, what is inverse integral kernel? because we have a kernel and what is integral. The first what we have in our mind is, okay, this is like transpose kernel, but can be something which is more general than the transpose kernel. Yes, it can be introduced like Q inverse of K. And it means that if I have some Q, then K integral kernels, Q is on X. An integral kernel Q prime is said to be Q inverse of K if this equality holds. Yeah. So they are somehow related, but the result is another kernel on this. Okay, this kernel could be just x is 1, otherwise is 0. So, but this is very special case. But the problem is that this k prime is not determined uniquely. Yeah, so we have more k primes that we have q inverses. So here is example. I will skip this example. Even if we have ki that is the set of all q inverses of k, the union is q inverses of k. So it means that there is like maximal inverse, q inverse. Some determination of q inverses, if we have a q and k, and so if k prime is determined by this formula, k prime is the maximal q star inverse of q when q star is defined in this way. So from q, we can determine like if we have q, which is some kernel on x, and some k, we can determine the inversion and the inversion to k with respect to some q prime. Sorry, q star. Just several theorems. If k is integral kernel, then kt, the transpose of k, is the maximal q inverse of k. And some other, what is interesting, let k be an integral kernel and let k, the inverse, be a q inverse of k. Assume that k is p inverse. Oh, yeah. And k is the p inverse of that. So from both sides, that k is q inverse. This is q inverse to k, and k is some p inverse to that. So if q and p are reflexive fuzzy relations, then this k is, yeah, perfect. Now I will skip this, and what is very important here is preservation of constant functions by lattice integral transforms. So I have two conditions. Here is some like formalization. What is C1 and C2 condition? But C1 is condition under which this fuzzy transform preserves constant functions. C2 is that this this lattice transform preserves integral transform preserves constant function. Now, because time is running, I will go to like some conclusions. First, what have been proved is that the composition is greater than this integral transform based on Q, and we see that K, that the inverse here, this inverse to K is Q inverse. So Q is somehow determined or interrelate here. The same we get here. Then to measure, yeah, thank you. Then to measure the quality of the approximation, we introduce modulus of continuity in this way. So the map, which is defined here, E is some equivalence of X saying some, what is the neighborhood? What is the neighborhood between X and Y? So if I fix Y, E gives me some neighborhood, yeah? And this is called modulus of continuity. Because time is running, so I skip some details. But what we can show that the original function and this integral transform is similar when, when the B residuum is used in a greater value than the modulus of continuity. Here can be extended to the whole function like this. When I took like infimum, give me 1 minute more. No. Okay. Fine. Fine. Yeah, this is almost conclusion. So, the first result is that is greater than some modulus of continuity. So from the continuity, I can show that I get a better approximation. And the second one is that the relation, that the composition, so the reconstruction is similar to fx, to the original, than the integral of q square, yeah, of q square, when q square, q is again like the kernel which is used to determine the inverse kernel. So it doesn't depend on the function f, completely doesn't depend. So, and under some conditions, we can show also that is equal to f. Yeah. Thank you for your. Okay.
Dinner, and I ask your student, this or So let us continue with the lecture by fsta, and we should really start.
Okay.
Please, it's your time.
Okay. Hello everybody. Today I want to introduce to you our work with the combination between Fourier transform and Fishbone theorem for solving the nonlinear Volterra integral equation. Now I want to tell we plan to divide our talk into four sections. The first section would be the basic conception. The second is how we reduce the complicated of the original problem by Fourier transform. And the third one would be how we use Fishbone theorem on handle the nonlinear. And the last one would be some numerical experiment. Okay. As you know, Fourier transform is is very effective tool to in so many fields in mathematics and also in neural network, statistic image project. And today I want to introduce you to the new application of Fourier transform on the mathematical area, such as integral equation. And We used to successfully apply fuzzy transform for simpler integral equations such as Fredholm equation and also Volterra equation. And now we tend to approximate the non-linear Volterra equation. So we use the Fishbone theorem to handle the non-linear one. So here is the non-linear Volterra equation. And you can see that the K is the kernel, G is the solve function, is the given function. And phi would be the relate to non-linear stuff. And because the K, G, and phi are also continuous, so the unknown use that we're going to approximate is expect to be continue also. And here, this is the Lipschitz condition for the function phi. And for this Lipschitz condition, by Fishbone theorem, you can see that our problem have a unique solution. And this is Fishbone theorem. Yes, this is the conception of a contraction mapping. And this is Banach-Fishbone theorem. And now this is fuzzy partition, and I think that most of you already know about this as well. So I tend to skip it. Okay, and here in our result, this is the inverse Fuzzy transform, and we plan to express this inverse Fuzzy transform of F by this multiplication of two vector. With the vector F is the vector of components, and vector A is vector of basic function. And this is the important lemma, just like the distance between original function and the inverse Fuzzy transform function would be O S square, with H is like this. And now this is two-dimension inverse transform of two-dimension function. And again, we will express this function into the combination of metric of component F and two vector of basic function A and B. And you know, Fuzzy transform had a lot of kind of shape, and in our research we focus on triangular shape. And this is we already finished the definition of the conception, basic conception. Now I want to move to the next step, and I want to explain to you like what we're going to do next. What we're going to do next is you see, this is our our problem, and this is quite complicated. And what we will do next is we use Fuzzy transform to approximate this equation into the simpler version. And you see, for this part, it's easy. It's easy to approximate by Fuzzy transform. For this part, it's also easy. But for this part is quite complicated, right? So, we will call this part would be the operator R of phi U. And we will use Fuzzy transform to approximate this operator by Rn. Yes, and because we will leave the phi, the non-linear behind for Fishbone theorem. So now we only focus on how to approximate this operator R. So instead of drawing like this is quite complicated. So we will approximate RU. So we start with approximate RU. So now I will start with this. Here is the definition of Montero operator. Yes, and for my own opinion, this part is the most interesting part in for the whole paper. Okay, and I give this example, and I will explain why example is interesting later. Now, yes, here this is the R that I mentioned. This is the R that I mentioned. This look like this, and here we replace the function k and u with their inverse Fuzzy transform, and we got the C1u like this. And because it's the inverse Fuzzy transform version of RU, so we have this property because it's the inverse transform, inverse Fuzzy transform version. Okay, so we got this. And here is interesting part. You can see that this one is the magic. And if I express this magic, you can see that this is the component of the magic. And you see that this magic is quite complicated. If we put this magic compute directly here, would be very complicated to compute. So we replace this magic by this diagonal magic. And the interesting point here is these two magic is not convergent to each other. Because you can see that the distance it will be h distance in here also be s/3, s/6, and 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 then the number of rows and the number of column of the magic also n. So they are not convergent to each other. However, if we put we replace for C1 the first magic, and for C2 I replace by the second magic. And the interesting point here is C1 and C2, they are convergent quite good, with the convergent degree would be S squared. And this is, for my own opinion, is quite interesting. And here is operator P, which once again this is the final approximate. Like we replaced for C2, we replaced this multiplication of this magic by this combination, and and again the distance between Rn and C2 also as well. And from this, and finally we got this, and we already find the approximate operator. And you see this operator is easier, like it's simpler compared to the original version. Yes. And here let's compute at any partition point tk, and well, we will express RNU tk like this. And when we put this again, into the original function, and then we have the original function problem can approximate by this. And you can see that how similar it would be compared to this one. And from now on, we're done with fuzzy transform, and then the next step would be Fishbone theorem. Okay, and here, okay, is the find the partition. First step, find partition. The second step is the fuzzy transform and compute new KG. Okay, and this one in Fishbone theorem, here we choose the first function u0 would be gt, because in here only gt is a given function that we know, so we choose it like the first function, and we use the approximate, of course. Again, we put this u0 and head into the left side of here, in here, and then we have u1 and head, and repeat the reduce and for m time, and we have this approximate. Yes, and the question here is how long and how many times that we can repeat. Actually, as much if we read the larger MB, and the better solution approximate is would be like M is large and the approximate is better. However, if in this theorem, this is final theorem, this is the main theorem. Okay, if we choose M is like this is the floor. This blanket is the floor function. If we choose M like this, then the arrows would also be as well. But however, for my own opinion, if we choose M larger than this one, this is even better. The conversion also even better. So in my example below, I choose M equal to N. Yes, and this is my example. This is the kernel function. This is the given function G, and this is exact solution U. And here, as I described before, I choose M and N equal to each other. And in here, I consider N equal to 10 and N equal to 20. And this is the errors between the exact solution and approximate solution. And you can see that these errors would be quite small. It's 10. This for me is quite small. Okay, so well, the conclusion, what we get after this, first we have the successfully combine a fuzzy transform and Fishbone theorem, and to solve the quite complicated integral problem. And in the future, we plan to extend to more complicated problems, such as maybe partial differential equation or something. And yeah, this is the start. And then, okay, this is what we consider reference. And okay, so my talk is done.
Yeah, 1 minute for questions, so please ask. I didn't understand the equation 2.3.
2 from
Why you have is t 2 times once in AT and once as argument? here is the extent, here is as an argument. I you use it. Or is it a denotation for function only? Yeah, but you use it 2 times for 50.
Yeah, but
That it would mean that
it's not the variable integration. But yes, these parameters. Yeah.
something that's fixed and something that's
Yeah, so you want to get rid of.
yeah.
So okay.
Yeah, if you want the middle better.
Yeah, okay.
Yeah. Then, so the answer is not so welcome again. And repeat once more the announcement that you should register for bus trips as soon as possible, but not later than 9 a.m. tomorrow. So,